Hello students, in this video we'll discuss a sequence of inequalities related to limsup and liminf of quantities involved in the ratio and root tests. Let's be given a sequence of non-negative numbers Rn, and let's assume they're actually strictly greater than 0 as well. We have the following. We have that the liminf as n goes to infinity of Rn plus 1 over Rn is less than or equal to the liminf as n goes to infinity of the nth root of Rn. Now the liminf is always less than or equal to the limsup of that quantity, so I can put a limsup over here. N goes to infinity of the nth root of Rn. And that's less than or equal to the limsup as n goes to infinity of Rn plus 1 over Rn. And all these quantities are salient quantities when we're dealing with the ratio or root test for the convergence of an infinite series. All right, so one of these inequalities in this sequence is trivial. This, like I alluded to earlier, this innermost inequality is trivial because the liminf is always less than or equal to the limsup. So that one we get for free, right? So let's focus on this next intermediate inequality over here. And so what we're going to do is we're going to, if, for example, this liminf was infinite, if that was infinity, then everything would be, then this inequality is trivial, right? So we're going to assume that this is equal to some number beta, which is less than infinity, okay? So in other words, this limsup over here is equal to a fixed number beta, right? So now what we're going to do is the following. We're going to let epsilon be greater than 0, and pick n such that if n is bigger than or equal to this number n, we have that Rn plus 1 over Rn is strictly less than beta plus epsilon, right? In other words, you're always going to be strictly less than that for n bigger than or equal to that number. Okay, so in other words, this ratio over here is always going to be less than or equal to the limsup past that point in the sequence. Okay, excellent. Because we know that sometimes that ratio can jump over the limsup, but eventually that ratio has to be less than or equal to the limsup plus a little bit more, right? So we can always guarantee this. And so now what we're going to do is the following. So now we're going to write this. So this is true in particular if I plug in n, right? So now we can say that Rn is Rn capital, then Rn plus 1 over Rn times Rn plus 2 over Rn plus 1 times all the way down to Rn over Rn minus 1, like that, okay? Because I read it as a telescopic product over here. Now what can we say about each of these terms over here in this sequence past the level n? Once I know that n is bigger than or equal to n, all those terms over here in this product, of which I have n minus n capital, are less than beta plus epsilon. So this is going to be strictly less than r to the power n, r sub n, and then I'm going to have a beta plus epsilon to what power over here? To the power n minus n capital over here, like so. Okay, excellent. Now, the nth root is a monotone function, so I'm going to take the nth root of this inequality over here. So if I take the nth root of the inequality, this implies that nth root of Rn is strictly less than Rn to the 1 over n power. And then this expression, beta plus epsilon to the 1 over n power, so that's going to be a 1 minus n capital over little n, okay? Now we know from a previous video that for a fixed number, a to the 1 over n converges, as long as a is not equal to 1, a to the 1 over n converges to 1, right? And if it's equal to 1, we clearly get that. So now I have an inequality over here, so I'm going to pass this inequality to the limsup. And so we're going to need a lemma for that. And of course, the lemma is something easy to understand, right? The lemma states what? It states that if I have two sequences, given two sequences, an and bn, with an less than or equal to bn for all n, then this implies that the limsup, as n goes to infinity, of the ans is less than or equal to the limsup as n goes to infinity of the bn's, right? That just follows the limsup is a monotone operator, okay? And so now if I take the limsup of this inequality, what do we get? We get the limsup as n goes to infinity of the nth root of Rn is less than or equal to, because we have to put an equal to sign if it's strict, the limsup as n goes to infinity of Rn capital, that's a fixed number, to the 1 over n, and then beta plus epsilon. I get 1 beta plus epsilon, and then I have a beta plus epsilon to the negative n over n, and n capital is again fixed, right? So now as n goes to infinity, this quantity goes to 1, this quantity stays put, and this quantity goes to 1, so this is equal to beta plus epsilon. So what have we shown? We've shown that for every epsilon greater than 0, the limsup as n goes to infinity of the nth root of Rn is less than or equal to beta plus epsilon, and that implies that the limsup as n goes to infinity of the nth root of Rn is less than or equal to beta. And that, of course, is this quantity over here, so we've just proven this inequality over here. So that gives us a proof of that topmost inequality. And now we're going to apply similar reasoning to the bottom inequality over here, okay? So what are we going to say? So similarly, if we want to prove this inequality over here, we're going to say that what? We're going to have the same epsilon. I'm going to pick what? Pick n and n. Let epsilon be greater than 0. And pick n and n such that what? Such that Rn plus 1 over Rn is going to be bigger than or equal to, let's call that liminf. If the liminf is negative infinity, again, it's trivial, so let's assume it's some finite number alpha over there, is bigger than or equal to alpha minus epsilon, like so, okay? Again, that tells from the definition of the liminf. Eventually, you have to be a little bit bigger than the absolute, they have to be bigger than, a little bit bigger than the smallest that you can possibly be, right? Okay? All right, and so now what can we say? Now we can do the same trick, right? So now we can say that Rn is Rn capital, and then Rn plus 1 over Rn times all the way down to R little n over Rn minus 1 by the same exact factorization. And now each of these terms over here by assumption is bigger than alpha minus epsilon. So this is bigger than Rn, and then alpha minus epsilon to the power what? To the power n minus n capital. I'll take the nth root of both sides again. So taking the nth root, we can conclude that nth root of Rn is bigger than the nth root, because it's a monotone thing, the nth roots, and these are non-negative numbers of that fixed number Rn, right? And then an alpha minus epsilon to the 1 minus n over little n, right? And now I'm going to pass to the liminf, right? Because the same sort of inequality is true over here. If one quantity is bigger than the other quantity, the liminf of this quantity that's larger is bigger than or equal to the liminf of that quantity over there. So now what do we have? So now I can say that the liminf as n goes to infinity of the nth root of Rn, that's going to go to 1, and then these terms over here are going to go to 1, is bigger than alpha minus epsilon, and that's true for all epsilon, and so that implies automatically that the liminf as n goes to infinity of the nth root of Rn is bigger than or equal to alpha over there. And since alpha is this liminf, we get this inequality over here for free. We're going to see in further videos how these inequalities can actually, every step in this inequality can be strict in some sense, and that will give us information about when we can use different quantities in terms of the ratio test or the root test in particular instances for infinite series convergence tests. Thank you very much.